Video 2 for the linear motion unit. Okay, so in the last one we talked about Aristotle and how Aristotle felt that there must be a force moving everything. So if something's moving, there must be something pushing it. And he had to reason the fact that there must be some sort of vacuum pushing arrows to keep them moving. Um, Obviously that's wrong. So we're going to jump ahead a little bit in history. We're going to come to another person named Copernicus. Um, you know, by this time, Aristotle, his views have been well established for hundreds of years. So we have this astronomer named Copernicus, and um, he reasoned that the Earth traveled around the sun. And here's how he came about this. He followed Mars. He watched Mars go around. Now, if the Earth is stationary and someone is standing on the Earth watching things, stars should go around in that kind of a path, because as they view, if the stars are going around the Earth, it should be a perfect path. However, Mars did something funny. It did things like this. It had these little tiny twists in its path. And the only way you can explain that is if Mars is going around the sun and the Earth is going around the sun, and those little twists comes from the fact that, well, as the Earth and the Mars go around the sun, they're going around the sun at different speeds. So because we're going around at different speeds, it makes it appear like Mars is following those weird little paths. So from that data, Copernicus reasoned that Mars is going around the sun, and therefore the Earth must be going around the sun as well. And this was completely against what Aristotle believed, and therefore what the church believed. So he waited until the end of his life before he published his findings, and he did this for two reasons. He feared persecution, and that's completely legitimate. In fact, when he finally published his book, he received a copy of it on the day he died. So he waited until the last minute. And once it's published, the church went around and burned many copies of that book. So his fears were not unfounded. Secondly, and this one I feel is the most dangerous thing, he had doubts. Aristotle's views had been taken as fact for centuries. That's really, really hard to overcome. It's really, really hard to convince yourself that something's wrong when it's what you've been taught in your entire life. But here's somebody who had scientific evidence, and his feelings and thoughts were overcoming the scientific evidence. And I think we see that a lot, especially in today's society, where we're studying things like global climate change and things like that. We have scientific thought, or we have scientific data, but for some reason people's thoughts and feelings seems to trump scientific evidence. I feel that's kind of dangerous. So after after Copernicus, we come to another scientist named Galileo. And Galileo finally gave credence to Copernicus. But to do this, he had to discredit Aristotle. And that's really hard to do. Now, he was not the first to point out the difficulties in Aristotle's views. I mean, remember, everyone had trouble with violent motion. They could tell that was wrong. However, Galileo was the first to provide experimental evidence to help prove his thoughts. So first off, what he did was he used the Leaning Tower of Pisa, and he dropped objects of various weights from the top of it. Now, the reason why he had to use the Leaning Tower of Pisa is so that when you drop something, it doesn't hit the building on the way down. Plus, it was one of the tallest structures around. So it was kind of cool. He would take two objects that were the same size but different weights and drop them. And it was very clear that they fell at the same rate. So this was pretty, excuse the pun, groundbreaking. Um, he would draw crowds, many, or very large crowds. He would draw so many people and then show them that objects of different sizes and different weights would fall and hit the ground at the same time. So this completely went against what Aristotle believed. There again, sometimes people would walk away still disagreeing with him, which baffles my mind. That was the first thing he did. The next thing Galileo did was he used inclined planes. Now, remember, Aristotle was an astute observer of nature. He dealt with problems around him rather than abstract cases that did not occur in his environment. So for Aristotle, air resistance and friction were always there. Motion always involved some sort of resistive medium. Aristotle did not believe a vacuum to be possible, so he did not give it serious consideration. So it was basic to Aristotle that an object requires a push or pull to keep it moving, because he didn't think about, okay, well, maybe friction is taking energy away, or maybe air resistance is slowing it down. It was this basic principle that Galileo denied when he stated that if there was no interference with a moving object, it will keep moving in a straight line forever. No push or pull or force of any kind is required. So here's how Galileo tested that hypothesis. And this was kind of a thought experiment as well. If you let a ball roll down an incline, it's going to speed up. If you roll a ball up an incline, it's going to slow down. So here's what he reasoned. Okay, what if I got a ball moving on a horizontal plane? There's no down incline to speed it up. There's no up incline to slow it down. So it must move practically forever. And he reasoned then that the only reason for it to come to rest is because of friction. So he tested this by using different surfaces. And he noticed that when the surface became smoother and smoother and smoother, there was less friction, and the motion of the object persisted for a longer amount of time. The less friction, the more the motion approached constant speed. So he reasoned then that in the absence of friction, if we were to remove all friction or other opposing forces, a horizontally moving object would continue to move forever. So here's another way he kind of tested this using ramps. He set up a ramp, and he noticed that when he released the ball as it rolled down the ramp, once it rolled up the other side, it came pretty close to the same altitude that he released it. So, okay, well, let's make the ramp a little longer on the other side, and let's lower the angle. The ball still came pretty close to reaching the same altitude. So he reasoned then, if I make it so that the ball never reaches the same altitude, so there's no other incline, it must keep moving forever. And that the only thing, in the first two cases, the only thing keeping, that kept the ball from reaching the same exact altitude was friction. It must be friction that was slowing it down. Now, for these ramps here, they're all starting from the same height for all cases. So the speed of the ball at its beginning is the same for all cases. So in the absence of any slowing forces or retarding forces, the tendency of the ball is to move forever without slowing down. This is something very important. This is called inertia. Inertia is a property of matter, and it's the tendency of an object to maintain its state of motion. So, as an application then, Galileo's concept of inertia would show that no force is required to keep the Earth in motion. So the Earth is moving, and there doesn't have to be a force pushing it. That's very, very important. This opened the way for Isaac Newton to synthesize this view, or synthesize a new view of the universe. Isaac Newton was once quoted to say, "If I have seen farther than any other man, it is because I stood upon the shoulders of giants." And he was, giving credit to Galileo and even to Aristotle for helping him develop his ideas for motion that we use today. All right, that concludes video 2.